Sounds like nothing just yet. All right, where are we? 25th. Okay, trees. That's right. We started talking about trees last week. All right, so let me just grab the link we have for trees section. Do you have any questions about the terminology? All right, siblings, parents, children, that fun stuff. It will take sounds to mean nothing. All right, so a tree is a directed acyclic cyclic graph. It's going to be a collection of vertices, aka nodes, are linked together. And we'll typically see a nonlinear structure growth. And it's like we talked about last time, a binary tree is going to be most common. Most commonly used tree will be a tree structure that allows for as many as 2 children per node. All right, so typically have a class node. We'll have a data section and we'll have link 1, link 2, typically named left and right. Assuming it's linked base. All right, you have a class tree and it will have a root node as for its data part structure. But doesn't necessarily have to be linked together via pointers. You can also have array-based trees. An array-based tree. The root is the first index in the array. The left child is 2 times the index plus 1, and the right child is 2 times the index plus 2. All right, so let's do a drawing here. All right. So at the top of the tree, we have a root. And let's say it has some sort of arbitrary value, A. And we'll create nodes. These nodes will link together. To show relationships. Each node is a root of that particular subtree, right? So B is the root of this subtree. You can have various children in its structure. All right, just arbitrary labels. And we'll link them together. So this is going to be a binary tree. And we'll add one last child over here. All right, so root node has no more than 2 children. So this particular part of our tree is observing a binary tree rule. Then we'll go ahead and go look at B. It has 2 children. All right, so this part of the tree, the subtree, is observing rules of being binary, and same thing with this particular part of the tree with D and F as the nodes there, and then same story here. And then a leaf node down for C, E, and F. Extra C's in here. All right, we're gonna make a G here. There we go. They don't necessarily all have to be unique in the tree structure. I'm just labeling them uniquely so that when I say C, we know which particular node we're talking about versus F type thing. Nope. The root doesn't necessarily have to have 2 children, right? I could have, let's try that again. All of that could be not part of the structure. There'll be a binary tree. It's just not very balanced in the way it is structured. This same tree as an array. That's good enough. So the index, and we'll have our data. So at 0, we will have our root value. So we'll have A here. A's left child is B. Current index from A's perspective is 0. 2 times 0 is 0, plus 1 is where its left child B would be. Root right child C, same thing, 2 times 0 plus 2 gives us where C would be in the array. Move along to B. B in the table is at index 1. 2 times 1 gives us 2 plus 1. So its left child G would be at index 3. All right, D, 1 further. C is at index 2. Left child would be at index 5, but there's no left child, so we'll skip that. Then we have its right child at E. G, all right, is at 3, so it's going to have 7 and 8 as its children, but there are no children for G. D is at index 4. All right, times 2 plus 1 gives us 9 for F, and this is our binary tree, simply with an array-based implementation sitting behind the drawing, as it were, for what the tree is. It doesn't have to be a binary tree. The same pattern would apply All right, so whatever the n is, right, so for binary, we have 2 times I plus 1, and then 2 times I plus 2. All right, so for a ternary, it would be, if I could type correctly, same pattern, 3 times I plus 1, 3 times I plus 2, and this is our 3 children, 3 times I plus 3, right? And going down to n-ary, n times I plus 1, right, all the way to all the way to however many there are, n times I plus n. Right, so the index is always going to be the first position, and then the levels of the tree, right? If we look at, so level 0, our topmost level, where we have our root, we have our 1 node. Then the next level of the tree will be the next 2 elements. The next 4 elements will be the 3rd level of the tree. And the next 8, is that 8? Looks like it. Next 8 elements would be the 4th level of the tree, and so on. All right, so the question, there will be a lot of empty slots as the tree goes larger. So if we're using an array for just a general binary tree, yes, there could be some discontinuities in here, some fragments, but places where we'll typically use an array-based tree are going to grow in a level-by-level mechanic, specifically the binary heap. And in that scenario, there will not be gaps in its particular growth pattern. All right, so let's talk about the heap, since it is our first implementer of. It's the only one we talk about this class. I don't remember there being a second one. And then the 2 flavors of our heap. All right, so binary heap is going to be a binary tree that has its binary tree. It is going to be array-based. It's array-based. It is going to grow level by level, and it is ordered. So ordering is in an up to down pattern. All right, so for a max heap, the root is greater than or equal to its children. Or we have the reverse, a min heap, the root is smaller than or equal to its children. Right, so the growth pattern nodes will fill the array from left to right, which is level by level, as a new data point is added at the count position. We'll look at the parent's value. That value does not adhere to the heap ordering. We'll swap parent with child, and repeat. Repeat. Looking at the parent until we get to the root and have no further to go. Okay. One sec. Okay. So we'll do this two ways. We'll do it as a drawing, and then we'll do it as an array. Uh, yeah. Well, no. I don't think family age-based growth would quite fit in this model. All right, so we'll do a max heap. Start whatever our first value is. Just call it 22. All right, the tree's empty. The root at index 0 counts 0. Go ahead and insert. So our count before insert goes from 0. We'll insert at index 1, and then our count goes to 1. We'll add a new data point. That value is less than its parent, then we're good to go. Right, so at index 1, we'll drop 15, and then it'll compare it against its parent, which will be a mathematical calculation as well. Right, it's just the reverse of that 2i plus 1 plus 2 pattern. Look at our parent. If the relationship is good, we'll leave it as is. And then our count will go to 2. We have 2 nodes in the tree. Insert our next data point. Add some data. Drop in our value 30. 30 does not like the relationship pattern. So what we're going to be doing is basically following a density gradient, if you want to look at it that way, where larger values want to float up to the top. So what's going to happen here is 22 will make way for 30, and 22 will slide down. And then our count will go to 3. So our count tracks for us where in the array the value wants to go. And we will track things that way. Okay. Well, if I can make this thing not clickable, I can actually drag, select things or not. Do. Well, we'll do it this way. We'll delete it, copy, undo, bring it back. That's not a terrible workaround. All right, next data point. We'll go ahead and do 22 again. Heap doesn't mind duplicate values at all. It's perfectly fine. When we look at the binary search tree, we'll see that the binary search tree is not happy at all with having duplicate values, but our count is 3, so index 0, 1, 2, 3. This is where we want our new value to get dropped. It will calculate where its parent is and then compare the two values. And we'll see that the relationship is no good. So they will swap, and I'll go ahead and look again, look at itself and its parent, see if the relationship's good. If it is, then we're good to stop, and our count goes up. All right, we'll create another node. Give the value 44. All right, our count is 4, index 0, 1, 2, 3, and 4. This is where in the array it wants to go. It will compare itself. See if I can get the selection here, and this one will show as multiple steps. In fact, we'll give this one its own new image. Well, that doesn't work as great anymore. Do. Multi-clicked. Let's see. Question, after the 22 node tests against the 15, would it have to test against the root as well? Yes, it tested against the root and found the root pushed back harder than it could push. All right. So 44 is being added. It will push up, and it will push up again. So 44 and 22 will change positions. And then 44 will test against the root and find that the root is stronger in pushing. And our count will go to 5. So 44 moves up. Moves up and moves up after testing against its parents. Yeah, so we got questions for the binary tree. So forget this is a binary heap, which is a binary tree. So it's a more specific version of a binary tree. Sorts itself in descending order. So yes, we have a if we look at a particular path from root to a leaf, you'll see it is a non-ascending order, to be fully precise, which almost means a descending order, but this could be 44, 44, and 44 in all three of these nodes on the left branch here, on this left slope, and that's perfectly happy. That would be a non-ascending order, but descending order is pretty close to correct. All right, so the highest values are not necessarily on the left, right? Because if we look at these two nodes, right, I have a 15 lower, right? It's lower than this 22 and lower than this 22, and I have a 30. This 30 is greater than this 22. So there is no left and right relationship in a heap. All right, so what's the big O for this? Excellent question. What is the cost of adding a data point to a binary heap? All right, so step 1, determine where in the tree's structure we want to add the node. All right, so this is just start at the count index. So this is going to be big O1, constant time operation. And second step, I'm going to heapify newly added value into the structure, which means we're going to look at the parent of the current node, and swap if needed. And we're going to repeat that, compare and swap up to the root of the tree. Right, so the repetition will go for as many levels as there are in the tree. So let's take a side track here and compare how many nodes can there be in a given type of tree. All right. We will start with where is my merge? Just drop down here, borders, merge cells. Okay, so we'll just look at a binary tree, and we will compare that to a binary heap. And we'll have here's the height of the tree. All right, so remember that we have a couple of definitions for height. The one that we're going with in this class, and if you decide to use a different definition, you might have problems with the autograder because it's going to try to mark you wrong. The height of a tree is the length of the longest path from the root to the leaf. Right, so in a tree that has one node, it takes you 0 effort to go from the root to the leaf because you are already at the leaf. Right, so for a binary tree that exists, there's going to be one node in a height 0 tree. All the one node, that's the root and nobody else. Now, as a tree grows, as we add more levels to the tree, a 2-level tree at the minimum, in fact, I forget. Min-max. Move my height down here. Use a break on the pages. Right, so whether it's just a binary tree or a binary heap, in order to achieve a height of 1, we're going to need at least 2 nodes in the tree. All right, just to add a visual here, let's do some drawing. All right, so we had a single node tree, 1 level, and that's it, all there is to it. Go to our next bigger tree. Whether it's on the right or left, doesn't much matter. It's going to take 2 nodes to get to that height. Right, height of a tree, go. We're back to our stuff that we're looking at last week. Right, we have a height of tree. Right, tree height. All right, 0 height tree, 1 height tree. Then we got a tree that's too tall. And what we're doing is we're looking for the longest path that we can find from the root to the lowest leaf. So if I were at a leaf and we're on a node that's already on the 3rd level, the height of a tree will go from 2 to 3 type thing. Right, so the other way you can look at it is the number of levels minus 1. Right, level 0, level 1, level 2. So the number of levels in the tree and the height of the tree are going to be growing in kind with each other. Yes, the number of gaps So we have two gaps. So you can look at it from the negative space perspectives. How many lines do I need to draw to separate out the levels? To get to our maximum, okay, here. Oh, copy paste doesn't work on that. Oh well. Let's go ahead and draw. So to our max size. All right, for a binary tree, this is as many nodes as we can get to fit. And there's only two levels. All right, height A1. So our max will go 2 or 3 here. And everything's consistent between a binary tree and a binary heap at this point. For a binary tree, our structure might degrade quite poorly. So this is going to be a binary tree, just not very tree-like. Right, we have the root. The root has a left child. The left child has a left child, or just a right child. There's lots of different ways to have our tree degrade basically down to a singly linked list in its structure. So this still qualifies as a binary tree. It's just not a very good looking one. In fact, let's make it, let's try that again. At least quasi tree looking. Right, so left child and right child, either which way, there's 4 different possible minimalistic trees that we can have. That's going to take 3 levels. We want to get to the max scale. Right, each level is going to be twice as numerous as, I understand what it is. Let's try this one more time. Can I copy? Can I paste? I cannot. All right. So my circles are going to be slightly off. Right, first level we have 1. Second level we have 2. Third level we have 4. Fourth level we will have 8. And we're going to have our binary growth for the number of levels that can exist to cover our max range. Right, so 4 more than the previous. So we're going to have 7 maximum nodes or data points that a binary tree can hold if it has a height of 2. For a binary heap, when our heap is growing, I cannot possibly get to the 3rd level until the first 2 levels are complete. So until we have these 3 data points, the top section of this tree, the first 2 levels of this tree exist, we will not have another one here. And what we're going to be doing is we're going to be building from left to right, as we saw, based on the count. So the minimum number of nodes in a binary heap or data points is going to be 4. The max will be the same because it's still a binary tree. We can't have any more than 4 more data points in the lowest level. Then we can have 2 in the second and 1 in the first. As the tree grows, right, just a basic binary tree can grow quite poorly. On the minimum scale, so it's going to go straight up by 1. But the heap is going to fall into a range here. If we generalize it, fine, we'll just capitalize everything to the height of the tree. Now you can see this value is just 1 greater than the height, so height plus 1. This one's going to be a little bit more. This is where we have base 2 growth, right? 2, 4, 8, 16, 32. Right? Those numbers are just 1 larger than the values we have here. And so we'll have 2 to the h. Now let's see, capitalize it. capitalize it. And let's see if I remember what my superscript is. I cannot. Where is my superscript? Control, I hit shift. Okay. 2H. Let's see, do I need a +1 in there? I need a +1 in here. -1. So 2 to the H, where H is 0. 0 plus 1 is 1. 2 to the first power is just 2. Subtract 1 and we get 1. When H is 1, 1 plus 1 is 2. 2 squared is 4. Less 1 gives us the 3. All right, 2, going one more, we get 2 cubed. 8 minus 1 to the fourth, which is 16 minus 1 gives us 15. Over here, we'll just have our 2 to the H. And then the max is the same over here, right? So we had height 3, 2 cubed is 8, 2 squared to the first, to the 0. So what we have going on here is all the inserts for level 3, which includes nodes 8 through 15, will require us to go through 3 levels of comparison, at most, to settle the new data point. If we look at the next one, all the inserts, level 4, should be our range 16 to 31, will have 4, right, iterations. And if we continue this pattern, right, level 5, 5 iterations, but the number of data points, right, doubling the amount of work, but only incrementing the effort by basically a constant amount each time. That is logarithmic growth. Right? So logarithmic growth, logarithmic growth occurs when only a constant increase in work occurs as the data set doubles in size. So this particular step, right, repetitions, are big O log n in work. So we had a constant part at the beginning here to get to where we need to start doing our repetition. And once we got to the repetition step, that part happened in log time. All right, so adding is going to be logarithmic time here. Let's get rid of my extra page breaks. Okay. So the question is, why is heap min so much more than the min for binary tree? Because the heap has 2 rules, right? So let me state those directly. Binary heap rules. It is a perfect tree, which we'll go look at Wikipedia. There's a little bit of ambiguity in the definition of this tree, but specifically, it's going to be a tree that is built level by level and from left to right, and it has heap order, which is our up-down data relationship. All right, so we'll go on over the infamous Wikipedia. There's some stuff over there. Go to our binary heap. All right, let's drop a link. All right, it's been around for a little while here. All right, so we have the shape property and the heap properties, the two rules that we were just talking about. And then, okay, then we got over here as a complete binary tree, which we can see it's not quite what this image is popping up here. Fun things. All right, so the complete binary tree is the foundation of the definition plus filled from left to right. Some authors will call that a perfect binary tree, which is like a complete binary tree, but it's fun. There's a lot of terminology here that the English is definitely getting in the way of things. But building level by level is how things are going to be going here. So the leaves, consequently, are only going to be on the lowest two levels of the tree. We have our lovely O notations over here. Finding the minimum value, we're talking about a min heap, is constant time because the smallest value, or if it's a max heap, the largest value is at the root. Right, so you can see here we have a max heap. So finding the largest value is constant time, it's at the root. You have immediate access to what the largest value is. Deleting the minimal value, right? So delete is a predefined operation here in a heap, just like when you have a stack in a queue. Deleting from a stack, known as pop, happens at a predefined location. It's the top of the stack. Deleting from a queue happens at a predefined location. That's at the front end of the list, and in it, it adjusts the internal pointers as needed. So the same thing here. When we're deleting, the defined behavior for a heap is we're creating the heap in the first place because we want to have the extreme value close at hand, right? So this is like a prioritization line where we have different priorities for people show up in line who we're going to process first. We are going to process the highest value or lowest value as is appropriate, and that's why they get put there. And it's going to be logarithmic time for deleting as well, adding. See here, worst case, log time, right? Average. I don't know how close, often it's actually on the average, but often, right? We can just drop a value in there, right? 7's the newest value that was added in this tree, right? We can tell that 7's the newest value added to the tree just by looking at the tree structure, right? The last, most recently added value is going to be the rightmost node on the lowest level. And well, not necessarily 7 per se. It could have been 100 and it just moved its way up. But this is the last added node. May not necessarily been 7. And if it were 7, 7 is less than 17, it stopped. It took constant time to add to the tree. If it were 100, then that's where we got our log time because we had whatever value was here before and it had to slide down. So 7 was there before, it slid down. Then 17 was up here, it slid down, and 19 was in the root. It would have been 19. Couldn't have been 100 because 19 can't be in the root with 36 over here. But 19 could have been added, and we've gone close to getting to the root in this particular situation. Ooh, it almost feels like a good test question. What values may have been the most recently added to this heap based off the current state? All right, in that particular situation, 7, 17, or 19 could have been it. 100 could not have been because previous state of the tree would have had 19 at the root. Uh, let's see. Okay, so the 2n plus 1 plus and 2n plus 2 is where, no, let's go ahead and grab the tree from Wikipedia, and we can toss the question onto the notes. So previous question, where does 2n plus 1 and 2n plus 2 come from? That's where things are actually in the array, like this image has here from Wikipedia, which I'll paste in here. All right, so here is the actual array. This is how the tree exists in memory. So we have 100 at the root, 1936 are its children. You see the little lines that are popping around here. 100 takes you to 1936. 2i plus 1 is 1, and 2i plus 2 is 2. Then we have 1, who is 19. Its children are 17 and 13. 2i plus 1 gives us the arrow here for 3 and 4. 4 plus 1 and 2. And then 2 gives us over here to 5 and 6. And then so on for 3, going down through here. All right, so the exercise. Exercise. Given the above tree, what values could have been the most recently added value to the tree? All right, so 7 is the candidate. It could have been 17 and it could have been 19. We'll just go ahead and highlight that. Let's see. Well, there's a way to, we'll just put it as a comment. Put it as a comment. Maybe that will, and that's showing the comments on the right side. Don't want it. Trying to put here so that the answer is there, but not hidden, so you actually have to think about it. Whatever. I guess we'll have to leave the answer into the Discord when we discuss this tree. All right, so it can't be 100. All right, so if we want to visualize this tree, all right, so before this node got here, it is possible that 7 was up here. All right, then 17 would have been there, but 19 cannot be here because it does not accept 36 as its child. All right, so 19, 100 could not have been just added in this case because the previous state here, so in the previous state we're saying, well, 100 is not in the tree. So if 100 wasn't in this tree, then these values would have had to work their way back up, and that's not going to work. Yeah, so level by level, growing our trees as we go, and then we'll grow off to the right here, right? The next value, whatever it is, wants to go here. The next value, whatever it is, wants to go there, and so on and so forth until the level's filled. And then we will start building down this way. All right. Let's do another one. Or binary search, which is our other ordered tree. All right, so binary search tree. Binary search tree. This is going to be a binary tree to start. It's an ordered ordered tree. Ordering is from left to right. Left to right. Values lower than the root of a tree are going to exist in the left subtree. Values greater than the root of a tree are going to be to the right or in the right subtree. Duplicate values may not be allowed. All right, so building ABST. Step 1, starting at the root. Compare the new value to the root. If that value is lower than the root, traverse to the left. The value is greater than the root. Traverse to the right. Stop traversing when we hit an empty subtree in the direction we are attempting to traverse. And at that point, we will go ahead and add the new node as a leaf to the tree attached to the node we're presently at. All right, so let's draw that out. All right. So we will start off with an empty subtree. So there's nowhere to traverse to. And we'll give it the value 47. If a new data point that we want to add is, say, 75. All right, so we're going to go ahead and add 75 as our new data point to the tree. We will start at the root. We will see if the root exists. And that 75 is greater than 47. So we'll attempt to traverse to the right. There is no right to traverse to, so we'll go ahead and attach that node to the tree at that point. All right, let's see, our next value that we want to add is 54. We'll add 54 to the tree. Start the root. 54 is greater than 47. Traverse right. Compare 54 to this root of this subtree, 75. It's lower, so it goes left. And since there's nothing on the left of 75, we'll go ahead and attach it there. And we can come along and add 27 up next. As you can see, our binary search tree isn't necessarily growing particularly well here. All right, it has 3 nodes in it. It has a height of 2, right? 3 levels in this tree. It's not at all balanced. That's one of the things that binary heap has going for it. It is a balanced tree structure. And when you have a balanced tree structure, you're going to have logarithmic times for a lot of your operations, which is commonly the goal for what we're trying to do. Okay, 27. Adding that to the tree. That is less than 47. So go ahead and attach it to left because left subtree is empty. And we're good to go. And the tree can continue growing like so. Add another value. All right, we'll go for 62 or 65 as wants to type. Greater than 47, less than 75, greater than 54. So we'll go ahead and attach it down over here. All right, so the new node is always a leaf. So if I were to ask you a similar question here by a search tree, which values could have been inserted, or the last insert in the tree, it would have to be a leaf. So it'd either have to be 27 or 65 added to this tree. It couldn't be 54, couldn't be 75 because the standard binary search tree is not going to do any rebalancing of itself. It's going to be as it is. Looking up a value in a BST. Right, we're going to start at the root. Compare key against the root value. The same. Turn the data associated with the node. Otherwise, if not matched, we'll traverse either left or right until we hit a leaf and can go no further. All right, a couple questions. What happens if a value repeats? All right, things go real poorly if value repeats. 1 second. All right, so let's take a look at this tree. Duplicate values in a BST, binary search tree. Okay, things are going to be bad. Seems I copied too little. All right. All right, so before we get to the duplicates, let's see here. Before we get there, what range of values, assuming no duplicates, could I add to this tree that would end up in the right subtree of 27? Assuming integers, what's the smallest value? Let's break the question down. What's the smallest value that I could add to this tree that would be in 27's right subtree? I have a direct response. Anyone else have a number? All right, got several 28s, right? So 28 would be the smallest. 45 would also fit. And yes, 28 through 46 would be the entire range of values that could be added to 27's right subtree based on this current state. Right? It has to be greater than 27 and less than its parent in order for it to fit. Right? Same thing would apply here for 75. All the possible values that could be added to 75's left subtree have to be in the range of 47 to 75, right? And not counting values that are already in 75's left subtree. So trying to add 54 again or 65 again will give us some structural issues. All right, so let's say we did want to allow a duplicate. Say we want to add 54 again to this subtree. All right, so 54 is greater than 47, less than 75, and is equal to 54. So we want to add leaves to the tree, so it either needs to continue on, either on the left side or the right side of the tree. And whichever way we were to choose, it would want to be consistent. So going with the limitations we have right now, we'll just say left because it's going to be easiest. Here, we'll just say duplicate values will go to the left. So we have 54 over here. Okay. So what values can we add to this tree such that it would be in 65's left subtree? All right, so we have 55 through 64, right? Or if we're saying duplicates are cool, which they aren't, 54 through 65, since duplicates are going to the left. Well, not 54, 55 through 65. 55 through 65 if duplicates are being allowed, but preferably 55 through 64 would be the good values that this should happily accommodate in 65's left subtree. 54's right subtree. What values could be added such that they would end up in 54's right subtree? Right, as we've been doing this, we've been looking at the node in question and its parent, and it's basically establishing that range, right, 55 through 64. So same thing here, itself, 54 through 54. Well, there is no range of values between 54 and 54. Right, so we'll try to slam 55 in here, but 55 would end up, as we said before, in 65's left subtree. Right, so 55 doesn't fit over here, which means there are no values that could exist in that subtree. And what we do for subtrees, the way we notate that is with a triangle. Get my arrow to click. All right, this would be a null subtree. Null range of values could be accepted over here. Right, so when we look at the code for this, our sample code, right, my sample code will just simply reject. If you want to add it, it'll say, no, you can't. If duplicates are in fact needed, we can accommodate for that. We could add a linked list for dupes into the node structure. All right, so if we wanted to accommodate, if duplicates are allowed, here are the business rules. Whatever it is we need to support. All right, our node structure goes from data, left, right, and duplicates. It's just a node star list. All right, so when we do a lookup, the value that we return now here is far more complex of a thing returning back, because now we're returning back a list of values instead of a single value. Coming back here, but if we were to add, if we were to allow it, so in this case here, 54, the way we would do this, all right, instead of the null range, because it's impossible to fit anything between 54 and 54, right? There's zero space between 54 and 54. Okay, erase the board, drop it in here. And so instead of 54 popping up here, it pops up to the side as a list of nodes, right? So duplicates just link off in a third dimension, as it were, trailing behind the others, right? And we're simplifying the trees. We're just pointing out the key values, right? This could be like a student ID, Social Security. Well, Social Security number would be a terrible key value to use in the system because that is sensitive data. But employee ID, student ID, some sort of internal ID or hash value or whatever it is that we're using to look up these values in the tree, and then the associated data would sit behind that. All right, so there we have our linked list and duplicate values. Right, so there are 4 or 5 54s in the system. What it is, they would all just fall in that list, and the tree structure would not degrade and get to the state where this subtree is always going to be empty because I can't fit anything between these two numbers. Right, so as we said before, range of values that can exist in a subtree are going to be based on parent-grandparent type relationship here, just like range of values are in 75's left subtree, 54 and 65 fit because they are both in between 47 and 75. But no room between 54 and 54. So this has an empty range. That will always be an empty subtree or null tree. The pointer to that tree could never be set to anything, which is going to definitely hurt our rate of growth. So, big O or BST insert. Since the tree is not balanced, insertion is going to be big O N, right? Sample. Build a tree with the following values. 1, 2, 3, etc., 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 3, 4, 5, and 6. Right? We can even rearrange some of these numbers a little bit. There are a lot of combinations we can come up with for those 6 numbers, such that it ends up just being a lightning bolt of some fashion, a jagged line from root to end. Right? So giving a binary search tree builder a sorted set of data could be quite bad. Quite bad indeed. We'll look at some code for rebuilding binary search tree, because binary search tree does have some good stuff here. Let's go look at the code. Files. Where are our trees? Trees. Binary trees. Here's my download. Okay. Here we have our node structure. Everything nice and public. Everyone has access to it. Easy, simple integer data. Again, right? To make this realistic, we'd replace an int with the appropriate data type or make this a templated type to begin with. Otherwise, we have 2 pointer nodes, left and right. Our default constructor just sets left and right both to null. And our overloaded constructor takes a data point. It will default the left pointer to the null, default the right pointer to the null, and then just copy our values into our fields here. Questions so far on their I'll get back to balancing in a second here once we get down to our code. All right, that's the end of our node class. We have our tree class. It is going to have a root node, which really shouldn't be in the public section, but again, do not use our data structure code examples as necessarily good object-oriented programming ways of doing things because it's not. hardly encapsulating anything at all. Otherwise, we have a default constructor sets the root to null. There are a few different ways to add. It's all the same idea. Adding to a binary search tree is going down a branch of a tree. So it doesn't require recursion, but we'll see recursion in a few examples here. But our initial scenario, we have an empty tree and we set the root to that node and we're done. We successfully added it. All right, so we create the node, make that node the tree, and we're done. Otherwise, we'll set a temporary node starting at the root, and we will dig, traverse our way down, compare the data that we're adding to the current node that we're at, which is the root to start. If the value is less than the root of this particular subtree, then we'll attempt to add it to the left subtree if the left subtree is empty. If the left subtree is empty, we will set it right. We'll add it and we're done. If that's not the case, here's our traversal. Our temp node is now our node on the left. All right, so let's draw. All right, so the first we added whatever value. We add 17 and it's in the tree. Next up, we add 5. All right, 5 is less than 17. So we'll go and add that into the tree. And we're done. Because temp node left was null, nothing to add. We want to go ahead and add 2 into our tree. We start the root. This is temp. 2 is less than 17 and left is not null, so temp slides over here to 5. 2 is less than 5, left is null, so we can go and add 2 into our tree. Link them up. All right, going to the right, same thing. The data is instead greater than the node that we're looking at and the right subtree is empty, then we'll add it. Otherwise, we will traverse to the right. And if it's not less than or greater than, then it is equal to. So this if condition is kind of redundant. And we will return false saying we are not allowing duplicates in this particular structure. All right, same thing, just iteration first and then figure out where to set the pointer to newly created node. And one of these is broken because it's not using the appropriate aliasing. I believe it's this one's broken. Not properly doing aliasing where it's trying to do a pointer. And you can put in there way back when the point difference between, yes, just because you're passing a reference doesn't mean you're passing by reference. It's one of those fun things about parameter passing. Remember that the basic nature of passing an argument is via copy. We're using an assignment operator. We are copying a value from one place in memory to another place in memory. And if that value is a memory address, a pointer, we're simply copying that pointer. That means if we dereference that pointer, it's the same as if dereferencing the pointer from whoever called us, but if we try to set that pointer by doing things like this is only going to change our copy. Right, so feel free to try to play with this one and see why it's broken. But this line 26 is broken because we're using a star here and not an ampersand to use the alias syntax. Otherwise, a recursive thing. Same idea. This one doesn't have that problem because we're not manipulating temp. We're manipulating a pointer within temp, which means we're good to go inside that tree structure. Traversals. Traversals are pretty easy. And once you've got recursion down, Since this is not a linear structure, when we're doing a traversal, what we're going to be doing is wrapping around the code. So let's go back to one of our trees. Say we want to traverse this. Not that one. That one's got duplicates. Don't care about that one because that's not really. I'm sure there's stars where it is useful, but I haven't run across any of them. All right, so a traversal, aka we want to iterate through all things. If we have just an array or a linked list and I want to dump out the array or linked list, it's easy, right? An array, index 0, print out, index 1, print out, 2, 3, however many there are. Linked list, temp node equals the head, print out, temp equals temp next, print, next, next, print, print, print. All good to go, right? We don't have a straight line we can do in this tree here. So what we do is when we start with our traversal, we'll start somewhere and we'll typically follow a left to right pattern. We'll just go ahead and go to left node. And then it will do the same thing going to its left nodes. And if there's nothing there, it will go back, do a recursive call, unwind the stack frame, and then we'll go to the right nodes. There's nothing there, we'll go back. And once we've done all the statements in this particular stack frame, we go back to where we called us, and then it can go on to its next step, which in case will be the right, go to 75. It can go left to 54, which goes left to nowhere, so it comes back. It can go right. 65 goes left to nowhere, comes back, goes right to nowhere. It comes back. Then we can work our way back up the tree. 75 goes right to nowhere and back. And then we get back to our root and we're done. Right, so we basically build a road around the tree. Shrink wrap it and then vacuum seal it to make a line that just walks around the perimeter of the tree. Okay, so back to the code. All right. Let's see, where's the code? All right, so traversal. It's going to be a recursive function. We're going to be calling ourselves. Remind me, we did talk about recursion a couple weeks ago, right? Base case, production rules, recursive call. Or am I losing my marbles? All right, good. All right, so 254 here is our base case. We have two production rules in this function. One where we take the left node and one where we take the right node, which causes us to approach leaves, where the leaves would have no left child, or sometimes not even other nodes won't have left childs, and same thing, a leaf would not have a right child, and sometimes other nodes would also have not a right child. For the Biosearch Lab, no, we would not need to support duplicates, but if you wanted to allow support, perfectly fine to explore what that takes. All right, there's gonna be three flavors of a traversal. Typically, there's going to be some sort of consumption of the data when we get to a node. Question is, at what point do we consume the data? Most often, we'll look at the data first, but that's not necessarily going to be the case. Sometimes we want to look at it in the middle. All right, so we'll do our traversals on the tree in a bit here, right? So changing the timing of when we do the print would change that. And we don't necessarily have to go from left to right. Left to right is just simply the default. We could do right to left. We'll get to deleting a node here in a second. So when it asks me about balancing, so let's take a look at the balancing here before I forget. All right, so read, build, balance. So what we would do is we would build a sorted array, which we could do by doing an in-order traversal on the tree. And give it the sorted array, and then we will build the tree based off of grabbing middle values. All right, so we'll calculate middle index, grab that value from the array, and just call our insert function. And then we would do the same thing again, pass the array, a smaller range, grabbing the middle values because middle value in a sorted array is a great root because half the values want to fall to the left and the other half of the values want to fall to the right. It's approximately, depending on how even the count is at that point in time. And that'll keep the tree nice and flat. The flatter the tree, the better, because that means the fewer levels that we have to work our way through in the tree. But let's see here. Okay. So let's talk about the lab. Do you have a lab? Pushed to this week. We have a binary tree lab, binary search tree. Let's talk about those. We take a crack at them. All right, so the binary tree lab, this one's the array-based. All right, so if you don't give me an array-based tree, you can expect not to get full credit because this is going to be an array-based tree. All right, so the class has the array. It has a count. It's going to have an add function. All right, this is not a heap. All right, we've talked about the heap now because the heap is who is going to be the one that will typically use an array-based tree, but we're not doing a heap here. This is simply just a binary tree. It's not a binary search tree or anything more complex than that. It's just a flat vanilla binary tree that we're using an array to store the data. All right, so the add function, just take the count and then drop it in the array. So the first value goes in the first index, second value goes in the second index, third, so on and so forth. We're going to create a print function, which is going to do a pre-order traversal. Right? So we're going to work our way through the array, doing traversal, just like the code we saw here a moment ago. But in the case of a pre-order, what we're going to do is when we get to a node, we just spit out its value. So in this case, the root is always the first output. We'll see more of this after we take this lab time and a break. And then we'll go to the left subtree. The way that we calculate, we're the left subtree, right? 2 times I plus 1 is the left subtree, and then 2i plus 2 is the right subtree. That sort of makes sense. Okay, let's go ahead and take 10 minutes to work on this lab, and we'll take a 5-minute break, and then we will come back to it. Going on mute. All right. Let's talk a little bit more about our tree traversals. Right, traversing binary tree isn't going to be in a straight line, but it will be a linear process, as we'll have to touch each and every node inside the tree structure. All right, so we'll go ahead and create a tree. Make the image of it start, and then we will do it array-based style. Just add a few nodes to our tree here. Link it up and give some values in it. I will use the binary search tree to start. All right, so let's 84 at the root, say 29 and 97 as its children. 29 can have 14 and 48. And like we talked about before, this has to be between 29 and 48 to be a valid number. So let's go for 35 and 114. So our pre-order traversal. Pre-order traversal. What we're going to do is we're going to be visiting the root, and we'll traverse left, and then traverse right. So our output, this tree, we will start at 84, and we'll spit it out. Next up, go left to 29, visit that, spit out the value. 29, go to 14, and we will spit out the value. 14 has nowhere to go. We'll just put circles. This goes left, comes back, goes right, comes back, and we start at 14. All right, so our function calls here. Excuse me. All right, so we have our pre-order. Pre-order. Right, node star root. Yeah, base case. So if we have something there, f root, see out your data, whatever it is there. Pre-order root node left. And pre-order root node right. Right, so we're at 14. So 29 had call us with 29 left. So 29 left was our root. So the root here, we're talking about being the root of a subtree, not necessarily the root of the entire tree. So some people may prefer to name this something else as not the root to try not to confuse it from the root of the entire tree as opposed to the root of a subtree. So we're talking about node 14 in question here. So we're at node 14. right? The node exists. So we spit out 14. Then we call preorder root left, which is null. So it makes the call. It's null, so we don't do anything. So it's done. Then we come back, make a call with root right. 14's right is null. Makes a call. Not it's null, so do nothing. Come back, and then we're done this entire call. So we can go back to the caller where that's not working so great. Woohoo! Well, I guess that one. Okay, let's see. Let's get you out of the way. And we will now start drawing on the left-hand side. Okay, so now we're back at 29. Right, 29 has already spat out itself. We just finished the call on the left-hand side where we had 14. So now we can make the call on the right-hand side. Go ahead and call 48. So we're making a call with 48. The root exists, spit it out. So we output 48. 48 makes the call with its left. Takes us down to 35. We can spit that out. Loop around. Back to ourselves. Back to 48. 48 has nowhere on the right to go to. Back to 29. 29 takes us to where we started at the root. And now we can get on over here to 97. And then last output at 114. And we'll work our way back up to the top. Does that make sense? All right, for in order, we're going to move this step for when we're going to bother looking at the data. So when we start at the root, first thing we do is go left. And we'll keep going left until there isn't a left to go to. So this time I won't do a big loop because we'll actually go left. Then we'll output 14. We'll go right. And we're going to go here. Back up to 29. We can spit out its data. 29 can go right. 48 will go left. 35 will go left. No left to go to. So right, we come right back. And we can output 35. 35 goes right nowhere. 35 is done. 48's left subtree is done. So we now output its data. You may notice we have a pattern going on here. We are growing. 48 has no right subtree. 48's done. 29's done. 84's left subtree is done. And we can output its data. Rinse and repeat as we go. 97, no left. Spit it out. And we'll go ahead, go right. 14, no left. We will output the data. And everyone is printed out. 114, nowhere to go on the right. 114's done. 97's done. And 84 is done. And we have a nice sorted output. So binary search tree. will give you a sort of output. So if we did need to rebuild binary tree because we've decided that it's just terribly shaped, we want to try to flatten it. Right? We could build an array from the tree that is sorted, which happens in linear time. So linear time is much better than any other actual sort on a random set of data. Right? All sorts we've looked at so far, most of them were n squared quadratic time. A couple of them were n log n. That's only an average case and best case in one of our scenarios. I'll get to your question in a second after we do the post-order traversal. All right, so post-order. Let me grab a screenshot. In case that's wanted. Wise. We will do a post-order. Which is just going to move the visit step. All right, so with the post order here, basically go to the leftmost leaf and then consume it. And once it's consumed, we'll basically pretend like it's not in the tree. So we'll go left, and we have a leaf. Since we have a leaf, we can go and output the value, and we can kind of pretend like it's not there. All right, so that brings us to 29. 29 is not a leaf because we still have children that we haven't got rid of yet. Go left, found a leaf. And we can output 35. Pretend like it's not there anymore. All right, come back to 48. 48 is now effectively a leaf. All right, because when we go do its right processing, there's nothing there. Output 48. Or 8, if I can type it. 10. Like it's not there. Come back to 29, right? So 29's subtrees are completely processed. So 29 is kind of like a leaf at this point. And we can destroy it. All right, come back to 84. 84 is not a leaf. 97 is not a leaf. 114. Knock 114 away. Then we'll have 97, and then we'll have 84. As we wrap that up, make it like it's gone. 87, like it's gone, and then back to the root. And we can output its value there. So, it's a question about the lab. Right, so how do we implement our pre-order for the lab? It's our pre-order for the lab. Right, so the traversals are recursive in nature. So we're going to need base case. We're going to need our production rules. Since we're going in two directions, we got plural here, and of course the recursive call. Right, which case we're doing our traversals, we're going to start at the root. Any which way. All right, so in the case of an array-based tree, the root is at index 0. Now, let's so root. Yes, we just need one in. So the root in any. I think is what I said. Okay, so let's say the tree is and something like this. So for index, And we have our data, which I don't care what the data is arbitrary, right? Because we're not talking about anything in particular. All right, so at this point in time, we should have a count. We have 1, 2, 3, 4, 5. Or we have 5 elements in the array. All right, so while any index less than count is part of the tree. Any index greater than equal count is just part of the array. At best, we're not beyond the size of the array and not part of the tree. Right, so our base case, right? If the index we're looking at is not in the tree, then we stop this call. Right, so we'll add a test comparing the index that we're looking at here. Right, so in case an empty tree, if we were called reverse reversal on an empty tree, the count is 0. Index 0 is not less than 0, so we're done. Tree's empty. We don't need to do anything. Otherwise, we print out 5 and then make a call for index 1 and make a call for index 2. And if all we had was 5 at that point in time, right, we would stop. Right? Because the way that the tree is building, we're always building at the count. All the data is filled from left to right in the tree. All right. As we saw, if it's link-based, our link-based base case, the node exists. Right? And there's 2 variations. Some I prefer the more paranoid approach of test the parameter. If it is a node, do work on it. Right? The other way is to test subtree for making the call, which is also perfectly valid, right? We don't bother calling the recursive function if there's no work to be done on the node. So it's kind of a wasted stack frame to call something when we're giving it null as an argument. So some people prefer that way. Either way is perfectly good. So long as this function is private, you can guarantee that it's called correctly. But if your function is public, someone could just go ahead and try to call your function with a null parameter, and you'll get a lovely null reference exception. Yeah, the good old $1 billion mistake. Let me see. $1 billion mistake. There we are. Null references. Want to learn more about this? Or the inventor of C++ decided, hey, nulls are easy enough to add. Yeah, this is good. Believe that'll do it. Always Google. Don't remember this being the place that I saw it last time, but yeah, there's definitely many hits on here that talk about it. But it's all about null reference. Yeah, and it's called the $1 billion mistake because how many real world businesses have, their applications have had bugs, things have dropped down, the application just potentially dies because an attempt to dereference a null pointer, which you can't do. You can't go to something that does not exist. So just be mindful when you are writing your tree code, which is link based, or you have pointers floating around. It's always a good idea make sure your pointer is in fact a thing before you work with it. If it's not a thing, say, whoop, there's nothing here, and move along. Nothing to see here sort of situation. Okay. Traversals. Let's see. There, tree lab here. Make sure that we've done some better coverage here. We've talked about levels. Been talking about leaves and roots and all that fun stuff. Paths. We've talked about height. Remember there are multiple systems. Tree height. Let's see what our first couple hits pop up with what they're using as a system. All right, so you can see there are multiple systems here. This one's showing height 3, where it's the same as the number of levels. Yes, I have an ad blocker on. What do we got over this one? And no pictures. What a terrible website. Let's go to the good old Wikipedia. Right, so right here we have Wikipedia. It's using our style. It's saying this height of the tree is 3 in this image. But right, so they've got people might have been in here editing things. It's consistent at the moment now. Getting all fun mathy. But there was definitely a point in time where it had on the same page showing both ways, which is perfectly fine because it's 2 ways to count. Or at least there are 2 ways to number things, right? 1, 2, 3, 0, 1, 2. Since arrays are 0-based in C++, like most every programming language, we will also be 0-based, like I mentioned last week, I think. So a tree with 1 node has a height of 0. One of the reasons why some authors don't like that is because that means a null tree, an empty tree, has a height of -1. This is going to be 1 less. And as we add levels, our height grows by 1. So that's why there are 2 systems, because -1, some people don't like that. I think -1's perfect because, like, for example, if you do a linear search and you fail to find what you're looking for, right? -1 is the return to indicate that it's not there. And 0 is not a good return because that 0 is perfectly valid. It's the first value in the array. But it's almost on the range of preference. Okay, so that's our tree height. Right, we've been talking about our n-ary trees where most of our trees are going to be binary. Not the case for everything. How are we doing with the concept of airiness for a tree? Right? If we draw a tree and I ask you what's the airiness of this particular tree, you can look through the nodes and see if it's 2-ary, 3-ary. Wouldn't be a 1-ary because it's not really a tree at that point. That's just a linked list. Anyone still here? Right? Everyone's just doing well enough. Doing all right at the moment. We're starting to get down our fun terms. Yeah. Every section, we're going to have the same pattern. New terms to pick up on as we move through them. Right, and binary search tree and binary heaps going to be a couple of our ordered trees. So remember, just like we were talking about before, we can have an ordered array, right? Stack order is an order, queue order is an order, and sorted is an order. So there's different ways that we can order data, right? So we have a binary search tree, right? Binary search tree has an ordering mechanism to it, and in its particular way of ordering things, left to right. And then we have our binary heap, right? It's also ordered, but it's ordered in a completely different way. It's going up and down, right? So just like we have stack queues or just a sorted array, there's more than one way to order a set of data linear context, and it's going to be the same thing with our tree context. There's more than one way to order things. And left to right is going to be fairly common. Right, left to right, but heaps are quite useful. And so let's go into application domains. Right, binary trees are not heavily used too much, but for binary heap, well, let's see. Let's talk about the concept first. Let's talk about a priority queue. Go to Wikipedia, grab you the link for that. All right, as like most of our things here, we're talking about an abstract data type, which means that we're going to establish what the behavior is. Implementation is up to the developer. So we've been talking about abstract data types long enough now. Let's post a link to that. But the idea is we want to keep the data ordered in such a way that the item, the highest priority, is the one we take next. Right, and there's lots of ways we can do this. We could just do a regular standard queue. Right, so standard queue as a foundation anyways. Right, so when we enqueue someone into the line, they start by being added at the end, but based upon their priority, they'll keep on cutting the line until they run into someone with a higher priority. Right, so we'll go ahead and say that small values are higher priority. So we build a queue, link-based, array-based, whatever our preference. In this case, link-based would probably be way better, but we'll just put the numbers. So we'll add 12, right? So we have 12 on our list. We'll add 15, and then we have 12, 15. So 15 comes in the line, sees the person in front of them has higher priority, so they will just stop there. We add, someone say like 14. They come into the end of the line, and then they will get to cut up at a 15, so 15 gets to wait longer. That sort of thing. All right, add 17, attach to the end of the line, and we stop. So long as people with higher or lower priorities are being added, things are quick. We add 4. All right, they'll jump ahead of 17. All right, and then they'll keep on moving up the line. All right, so we're gonna have to basically do a bunch of iterations down either the array or linked list. If this was array-based, right, all these values actually have to physically shift in the array. If it's link-based, we're talking about the pointer. The pointer just keeps working its way down, which means we'll need a doubly linked list so that we can work our way in both directions, or we could just start from the front if we wanted to, keep it a singly linked list, and you just wait until we get to the end and add them at the end, or add them somewhere in the middle as it goes. Basically like maintaining it, the sorted linked list array lab that we did. All right, so there's several ways we could do this with a just basic queuing mechanism, right? When we dequeue, right, we just pull from the front. Whoever's at the front of the list, take the front of the list as they are the highest priority. Right, so NQ becomes a linear problem, and DQ stays a constant problem. Right, so we definitely have degradation over our standard queue here, because the standard queue, both of these would be constant time. All right, so our heap for priority queue. We've already talked about how adding works, so NQ, or add, big ol' log n time, and remove, which is taking the root. We haven't talked about that mechanism yet and how to actually do that, but we will. It is going to be constant time to get the value. All right, plus log time for restructuring. But that could be happening on a separate thread. We could immediately give back the value, and a separate thread could handle the actual removal of that value. All right, but it's not the only way. If we have a small range of priority values, right? So for example, we go like task manager, right? And okay, where are my processes? Right? So if we wanted to like set priority, right? So we have 1, 2, 3, 4, 5, 6, 6 possible priority levels, right? So that's a pretty small range of values that something could possibly have, right? So we could implement a priority queue as a collection. Priority queue could be handled as a collection of queues, right? So each priority level gets its own queue. Yes, yes, I like to use too many apostrophes. So for a given add, we'll look at the priority and just NQ to the corresponding corresponding queue. So that gives us big O one for all our operations. We're doing a proper NQ, proper DQ. And everything is all good to go. But if we have like a range, there's thousands or more possible priorities based off of the data point that we're using to prioritize things, right? That's where H can become too much. uh, priority queues do need to be careful about priority inversion. problems. 1 second here. Back when I was in college, a professor told me a story that the Mars lander ran into a software glitch where it had a priority inversion issue. And the Mars lander has multiple processes running on it, but it's going to have an operating system to operate the rover, and the different functions on the rover are going to have higher priority than other functions. But when you have multiple processes all trying to take a resource on the rover to do something, and you have variation in the priorities where you have a high priority system says, I need to move the arm, camera, go forward, stop moving, whatever it is. But a lower priority process has hold over that resource. It ran into a priority inversion issue where the high priority process wanted that resource. So it's very, very busily saying, I want the resource, I want the resource, I want the resource. I'm spending all of the clock cycles trying to get the resource and not allowing the lower priority process to actually finish what it's doing and release the resource. So you get a priority inversion problem. So we can run this problem where we have these 6 lines. We're going back to the task manager. We have our 6 priorities. So real-time processes are basically you get to come back up more quickly, right? In an operating system, right? One, multiple cores, there's gonna be a bunch of threads available, and higher priority processes are gonna get in line faster ahead of everyone else to get back into the processor. And depending on how much real-time work the system needs to do, it can get to the point where it starves out all our other processes where they never get a chance to do any work, even though their work might be important as well. So make a note to yourself, never mess with this stuff because you can really, really cause problems on your machine for if you try to set a real-time priority for something that actually wants to do things and it just keeps popping up in line over and over again, and everyone else says, like, oh, I want my turn. So just be mindful of things like that. Let's see. Doing some math in my head there. Okay. Let's continue with our binary heap operations. Deleting from binary heap. We talk about deleting from binary search tree as well. Where are we at here? 3.5. I'm not in the right spot here. 3.5, binary heap, deleting. All right, so deleting from the binary heap always happens at the root. This is our standard operation. Deleting from somewhere else is not the purview. We can talk about the practice test today if we want to. All right, so deleting the binary heap always happens at the root. Right, that is the defined operation. The whole reason of keeping the smallest or largest value at the root is so that we can get to the smallest or largest value very quickly. Trying to find someone else to delete is a linear thing. All right, so deleting some other arbitrary value from a heap is a big O N problem, as search is not a supported feature of the heap. Right, so for example, let's make a heap. And let's make some values. All right, make it a min heap. 4, 7, 7, 8, and 7. And impression shows arrows. Actually use a linked structure anyways. So do non-arrows. All right, so delete 7. All right, who should we actually delete? Right, there are a lot of 7s in that heap. Right, it's bad things. Just like adding duplicates to a binary search tree is bad for a binary search tree. Doing an arbitrary delete on a heap is just bad for a heap. A, because it's perfectly happy with duplicates, so now it becomes ambiguous as to which 7 are we supposed to delete. So delete for the above heap will yield us 2, and now we need to rebuild. All right, so 2 has been given back. This creates a void in the middle. So what we're going to be doing is, that's interesting dash pattern. All right, whatever. Feels small. Let's get some good dashes in here. There we go. uh, right, so a binary, yes, the early, I thought I answered the binary search tree in order traversal will always print from lowest to highest. Doesn't matter how the tree got built. You give a tree a set of any number, a set of numbers that exists in any order. You build the binary search tree, and then you run in order traversal. You will get a sorted list in ascending order. All cases. Okay, so deleting from binary search, binary heap, value of the root goes away. We are reducing the count. So reducing the count means that the rightmost node on the lowest level is falling out of the range of the tree. So remember, this is array-based. So let us get the array in here as well. We'll just do is text. All right, so we had 2 at the root, then 4 and 7, and the 7 again, and 8 again, and 7 at the end here. All right, 2 is going away. All right, so we have a space where 2 is, and after that, 7 7 is falling out of range because our count is going to be shrinking. Count will be going, what do we had here? We had 6, and it's going to be going to 5. So there's not going to be any room in the array for this position. So what we're going to do is we're going to look for a new root. So what we're going to do is look at the children of the void and the node that's falling off to see who is the smallest of those 3. Whoever's the smallest of the 3 will move in. And then we will go ahead and repeat the process. All right, so our void is moving 4 leaves that position, and we have a new void to fill. And we have 7, 7, and excuse me, we have 7, 8, and 7 to choose. So the void, all right, so 4 has moved here, and the void, now here we still have 7 trying to fall off. in our array. Right, so the 7 here that's floating off in space is the smallest, or in this case, tied for the smallest. So what we can do is go ahead and grab that 7 away from there and drop it in and be done. We could have grabbed this 7, dropped it in, and made the hole over here, and then the other 7 would just plop in over here. That'd be an alternate way, but that's just extra moving. So not much value in doing that. And then this 7 falls off. Let me go back to the previous one here because I did not underline the 7, showing it as wanting to go away. So we started off with 6 nodes and we're down to 5. The smallest data point is at the root. And when the bubble gets created, that bubble will move down the tree. And it's possible it goes all the way down the tree, but usually it's not going to go very far when things are happening here. But left and right relationships are not relevant. So it might go down. It's possible to go all the way down the tree, but it's very unlikely. Depends on if we have a bunch of heavy values on the right, and lower values on the left for that to be the case. But it can happen. Yeah, so the array, right? We have the array here. This is the array afterwards, right? There's no space in here. There are no voids in the array. Okay, so we have 0, 1, 2, 3, and 4 as our indexes, and that's what we have in the array. This is why the heap is array based. Right? The heap has the ability to know where its parent is. Just doing the math, reverse the math, right? I have to do the math again in my head, but it's like cut in half and then floor it. I think we might need to subtract 1 before we cut in half and then floor it. Get the index. We can look at that math a little bit later. And where this operation is happening, right? If we want to do our next delete, this node falls off because we can just look at the count. Right, so here our count is now 5. We're done. Right, so next 0, 1, 2, 3, 4. Right, so we can go ahead and shrink the count down as the first thing we do when we do the delete. And then we go at that index and say, yep, you're no longer valid index. We immediately know where 8 is, constant time, that this is the node that's going to fall off if we delete again. Right, so we can delete again. Perform another delete operation. Right, 4 goes away and 8 is falling off. Right, so we'll consider 4 an empty position and 8 a no longer valid position. So we'll go ahead and we'll make the count 4. Because we have only 4 data points at this point anymore. We're just making sure they all get to where they need to go. All right, so we have a void. We have 3 candidate values to take over here. We will go ahead and favor the right-hand side values when we have ties, because the right-hand side is going to be typically shorter than the left-hand side, so there's going to be less potential bubbling going on as we do that. So of these values, this 7 can go ahead and promote itself up there. And so we will move our void. If we go too far, let me see what proof says. All right, going too far. Leave that 7 there. Keep all our steps separate. Okay, fill the void with 7. Create a new void. So the void is now 7 and 0, 1, 2, 0, 1, 2. Lots of 7s here. Makes things extra fun. There's our new void. And then that node has no children. So there's only one value that can go into it. And our delete is completed. Right? So it's still a min heap. 7, 7, 7. That's non-descending. And we have 7, 8 non-descending lists. Right? Delete again. That 7 goes away. This 7 can jump in. Delete again. That 7 goes away. The other 7 jumps in. 8 ends up over here on the left-hand side. 7 goes away, and then 8 goes away. All right, so let's do that again with some discrete values. All right. That is not a good spot. All right. All right, 7 nodes seems like enough work for our heap. Okay, so let's uh well where we delete from just depends on the values, right? It could be coming from the right or the left. So we'll do 5, 10. Ugh, tab does not work. 7, 12, 15. Go for 8 and 19. All right, so our first delete 5 goes away. 19 is falling off. 7 moves up. 8 moves up. And 19 ends up 1 over to the side. Do a delete again. 7 goes away. All right, 19 is falling off. 8 is the smallest of, so it goes up. And then 19 works its way up the tree. All right, 8 falls off. 8 gets deleted. 15 falls off. Smallest value is 10. 10 moves up. Smallest value between 12 and 15 is 12. 12 moves up. And then 15 ends up over to the left-hand side. All right, delete again. 10 goes away. 15 is falling off. What happens if I delete 10? Well, 15 can't go into the root. because it's greater than 12. And since we're deleting, since the value is falling off from the 12 subtree, whatever value that's falling off here, unless it's a duplicate of 12, would not go into the root. All right, so 12 takes over, makes a void, and 15 will fill that void. All right, deleting from the root. 19 falls off. Smallest of those two values promotes up, and then 19 finds its way over there. And the tree shrinks. Value from the root goes away. 19 falls off and becomes the root, and then we have the empty tree. All right, and we now have the heap sort. Build a min heap. Destroy that heap. And building a min heap is big O n log n. And destroying that same heap is big O n log n. And we don't pretty much use it because we have other sorts that take just n log n by themselves without having to do n log n twice. Technically speaking, the heap sort, right, does not care about a coefficient. So big O would be n log n. Regardless, it has the same complexity, but the reality is it's more expensive to do. More expensive to do a heap sort. But it is one of the sorts we talk about because it is a way to do it, right? Because 5 was left, then 7, then 8, then 10, then 12, then 15, then 19, right? The values that we were fed from our heap were in sorted order, right? That, of course, presumes that the heap does not change during this process, because then that would cause it to fall apart as an actual sort. That gives us our heap sort. So deleting is a defined behavior for our heap. It's always deleting the root, whether it's a min heap or a max heap. If you wanted to do a reverse sort, right, you would build a max heap, and then the largest values would pop out from the top, and we would rinse and repeat. Let's see. Right, we could do traversals on binary heap, just the same as we could do binary search tree. I don't remember there being anything special about the output order for a heap, though. Yeah, nothing particularly special there. Let's see here. Binary tree lib. Everything we talk about there. Binary search tree, talk about adding there. All right, so deleting. Deleting from a binary search tree. That's what I was typing earlier. I was typing in the chat. Okay. Okay. All right, so any node may be deleted. When deleting from a binary search tree, there are 3 scenarios that may exist when we're doing that delete. First scenario, we're deleting a leaf. Second scenario, we're deleting a node with a single child. And third scenario, deleting a node with 2 children. All right, so deleting a leaf. Very simple. We'll just go ahead and set a temporary pointer to the leaf node. Set the parent pointer to null, and delete the temporary node such that we don't have a memory leak. Deleting All right, so deleting a node with a single child. What we're going to be doing here is we're going to be bridging the gap. And we'll talk about why this works at drawing some trees up here. All right, so we're talking about binary search tree. So we're going to have temporary pointer. Set a temporary pointer to the node being deleted, and we'll update parent pointer that is pointing to the node to point to the child of the node to be deleted. All right, so it's gonna take over for the grandma's gonna be taking over the grandchild. All right, delete temp. Deleting a node with 2 children. All right, this one's gonna be the complicated version. The first 2 are pretty easy programmatically and logically. This one, what we're gonna do is we're gonna delete by copy. We will find a replacement value from one of the subtrees of the node we're deleting. Copy that value into the node, and in turn actually delete the node we copied from. All right, so let's create a tree. With a bunch of values. Again, this is a binary search tree. So we have the left to right mechanics going on here. As we are doing the copying. So we'll create a fairly big tree here. So we do multiple deletes. From the tree. And put one here, enough, and one over there. All right, we'll have 100 in the root. No, we won't. My bubbles are too small. We will have 45. 22 and 71 will be its children. 22 can have 14 and 36 as its children. Let's get some lines in here, or lose track of my left and rights. All right. All right, 71 can have 62 and 83. 14 has 7 and 19. 19 will have 17 as its child. 36 has what? 40 and 38. 62 has 55 and 68. 83 has 74. All right. Any mistakes made? Do we see any node that is violating the rules of the binary search tree? Right, we have to make sure to answer the question right. We have to look at the ranges. So we have the root 45. So I mean, everyone to the left here needs to be less than 45. Anyone that's not less than 45 is breaking the rules. We can repeat that 22. Everyone to the left needs to be less than 22. Everyone to the right greater than 22. And since we already checked that everyone was less than 45 on our first test here, we don't need to bother worrying about that range. Right? 14. Same thing here. Everyone to the left is less than 7. Everyone to the right is greater than 14. We don't have to worry about it being greater than 22 because, again, we started at the top and we already validated everyone's in range here. All right, so on and so forth. 71, everyone less than 71, everyone greater than 71, rinse and repeat. All right, so that is our starting point. We will go for a simple case. We will delete 38. Deleting a leaf. All right, we'll fix the 40 pointer so it's not pointing to a node anymore, and 38 goes away. Delete is done. Simple case. Now we'll go ahead and delete 36. This is our second case. 36 has a single child. Right, so what we're saying we want to do is we want to change this pointer to point to 40. All right, so let's look at the logic of that, see how well that is sound here. What is true about all the nodes in the right subtree of 22? Right, all greater than 22, which means any node that we choose to be the right child from the 36 subtree, whether it's the node, it's 36's left node or 36's right node, it is going to be greater than 22. So that relationship is going to hold. So we can bridge over 36 and 40 is perfectly good with 22 as its parent because it was already a parent. It was simply just a grandparent previously. All right, now let's delete. Who should we delete? 22 or 71? We'll delete 22. 22. All right, so getting rid of 22. We can't just get rid of it because now we have, right? So let's say we try to. Boom. All right, now we have 3 subtrees. We could do this where this is another way we could do it where we just go ahead and have this point on the nodes and then this gets reattached sort of thing here. But that way it can get a little bit messy. So instead, what we'll do is we'll take a value away here. So we'll let 22 go away. And then we'll take a value from one of its subtrees to replace it, right? So we could take 40 over here and then delete this node, and it's a binary search tree. Everyone left of 45 is still less than 45. The change here, 40, everyone to the left of 40 is less than 40, and we're still good here. So that is an option, valid option we could use. A better approach would be to choose a node from the bigger tree. That way the bigger tree gets smaller and this binary search tree tries to stay a little bit flatter. But there are two candidates. So 40 was a candidate. No, we have 4 values in the left subtree. Someone is saying 19. Does anyone else think another number would work as the parent or grandparent of all the nodes in this subtree, such that they're all lesser than that node? Right? We could try 14. Let's see how well 14 works. Right? So we can copy 14 over here. Right? So before we fix things, which is going to require a lot more fixing still because we now have still 2 children. Our first problem with 14 is that 19 and 17 are both greater than 14, so they can't exist in its subtree. So the way to fix that, we'd have to do things like this, where we reassociate arrangements here. And yeah, it could be done, but it definitely causes problems with the rearrangement. That on top of the fact is that we have still 2 children to deal with here. So what we want to do is we are going to, when we're deleting from the subtree, we are going to start. So if we're deleting from the left subtree, we'll start at the root of that subtree and we'll just go right until we can't go any further right. So the rightmost node in the left subtree is 19, which is also the largest value. The rightmost node in any given tree is going to be the largest value in that tree, which means it's going to be greater than all the other values in this tree. So we could use 19 over here instead. All right, so we will copy that, which was the same truth for the 40 node. It was the smallest value in the right subtree of 19. It is the leftmost node, right? So if there were additional values still in this subtree, 41, 42, 43, 44, 40 would have been the value that would have brought it up here. So it's the smallest, and it will still be smaller than all the other nodes in the right subtree. All right, so we'll do that as our first step. 19 took over 22's position, and now we have either a delete a node that is a leaf, like we did before. If we had taken 40, we would have just blown 40 away and it was gone. Or we have a delete a node with 1 child, because if there were 2 children, we would still be going right, because we either go so far right that there's only a left subtree at this point, or it is a leaf node. So we've simplified the problem down to our simpler cases, where we just, bridge the gap. 14 would point over here, which I'll do via diagram by just copying it out, but it would actually point to that node, and then we would have deleted the node where 19 used to be. In fact, let me do that. Let's do it how it actually would be. Right, 19 got copied, just leaving it empty so it's easier to see when you look back at this diagram what happened. I lost my value. I had 14 over there. 17. Let's get 17 back in there. Get back in there, 17. All right, thanks for the help on that. All right, so 17 node, and then we'll just bring it back up in the drawing here. And things are looking reasonable here. All right. Let's do that again. We will delete the root. Delete 45. It has 2 children. So we'll have to go through the same process again. All right, 45 goes away. That gives us two candidates. We have either 40 or 55 to choose from. The largest value in the left subtree or the smallest value in the right subtree. And since the right subtree is bigger by node count, the heights are the same. There's two ways to look at that. Node count is probably going to be better, right? Because there's different ways of balancing trees as well. We'll get to that later. So we can go and choose 55 as recommended in the chat. All right, so 55, which is a leaf, which even makes this easier, right? 55 goes away. And back to a binary search tree. So we can double check 55. Is everyone to the left of 55? Less than 55, right? 19, 14, 7, 40. All good. Everyone to the right, greater than 55, right? Everyone's bigger than 55. It is binary search tree. So we're able to remove it. So finding the value. This is a binary search tree. We have no guarantee of balance with a basic binary search tree. Linear times. Pretty much everything in a standard binary search tree is going to be linear time because this could all just be a big old long linked list or very close to a linked list, right? So step one, find the node, but otherwise, best case, logarithmic time if the tree is fairly balanced looking. The tree is fairly balanced looking. We only have to go down to the height of the tree to find the node and figure out what rearranging we'll have to do at that point to get the tree back to being tree state with the loss of that particular data point. Let's see. Almost 9 o'clock. I had 10 minutes. I have 5 minutes break, so we still have 35 minutes of break. Yeah, all right. We take a 5-minute break, and then now we're just in the lab time here. We have the other lab, binary search tree. Let's talk about. So the binary search tree. Let's see if we need to fix any dates here. Min heap traversals. No, looks like we've covered everything. All right, traversal is just an exercise. You take the array-based lab and just do the other traversals as well. Pre-order, in-order, and post-order inclusive. And then we have the min heap, right? This is going to be your array-based tree. So you can take your array-based binary tree lab and then transform it to actually being a heap. And program 2 be pushed to Wednesday. Program 2, do. Wednesday next week. Sure, we can make it not do the same day as lecture. Because people have a tendency to procrastinate instead of attending lecture, they are working on the program, and that is not conducive to learning the materials from the lecture, right? So let's bump that out. Couple days, all right. While we're in the syllabus land of looking at the future, right? We'll talk about practice test after the break if you're interested in talking about that. Otherwise, I'll stick around. You have lab questions, stuck in labs, stuck in the program, whatever. We'll talk about that. I don't think we have any previous labs. When you talk about the sorting lab, was nothing special there. All right. We'll take 5. We'll come back at 5 after. Keep on talking to it. Good night to those taking off, and talk to you later. Otherwise, I'll keep talking to the rest of you who stick around. Nope. Just getting the screen prepped. But now the clock is 5 past, so we can go ahead and talk about practice test. After I finish sneezing, that is. All right. All right, so reverse push. Remember, select program run, 1, read operator, push it, push it, push it, plus 2 plus 3, 5% back on the stack. So we have 1 and 5 on the stack. After the operation is complete, so we have 5 and 1 as our stack state. 4 gets pushed, so we have 1, 5, 4. Okay, we'll draw. So we have 1, 5, 4 as our stack state after that. Do subtraction. So 5 minus 4 gives us a 1 and a 1 on the stack. Then we have a 5 multiply. Yeah, I should just delete that one. All right, we have 1, 5 on the stack. Then we have 6 and 2. 6 and 2. Then we'll do the divide. Gives us a 3. On the stack. Then we have 2 pluses. Gives us 8 plus 1 gives us a 9 at the end. All right, math. We'll have our base address plus we want 60, which is going to be 6 times 12 columns times 4 bytes per. So calculator survey says 6 times 12 times 4 is 288. All right, plus our 1200 gives us our 1488 for our math there. And see, this one's just the base address because we didn't go anywhere, 00. And more math. Same, same, same. Which sort is this one? All right, so we got a for loop, I equals 0. All right, standard for loop, and position equals 1. In position equals 1. Then we have j equals I plus 1, j less than n. All right, and we keep looking for, so we had our minimum value at the first position until we found someone smaller. Then at the positions, we set the position to j, and we keep on going there, and then we swap if necessary, right? So that was our selection sort. Which line of code is a recursive call, right? So line 6 has our function called a function. I've asked which line is the base case. That's line 3. Which line is production rule? In this particular example, that would have been also 6. Using an insertion sort. All right, so insertion sort. Our first number is the sorted value. Then we would grab 5 and it would shift things over. So 5, 8, grab 1, 1, 5, 8, grab 6. Right, we should have grabbed 6 here to put it in order here. So line 4 is not in the correct state. 6 should have been the one that pulled in next. All right, write code. All right, bubble sort. All right, so which numbers will be in a different spot after the next value is moved into sort position? So right now we have 77 already in its sort position. So we start over, 27, 42 is happy, 42 moves over. 42, 44 is happy, 44 moves over, and then 44 ends up over here at
Professor, we can't see.
okay. I will scroll up a little bit more. All right, so Ooh, it even scrolls off the side here, doesn't it? Let me go to the preview mode for this one. Scrolling is not good when it's horizontal. All right. Bubble, bubble, bubble. Still scrolling. That's not good. I need to make these boxes smaller. Yeah, at least I can see the numbers still. Okay, so 77 and 99 are in their sort positions. So let's draw. All right, 27, 42, happy. 19 will move over. 42, 44, happy. 25 moves over. 12 moves over. And we have 44. 44 there. All right, so 19's in a different spot. 42's in a different spot. 25, 44, and 12 are all in different spots. 27 didn't move, so 799 didn't move. All right, then we have insertion sort. Which numbers will be in a different spot? All right, so 27 is not the small insertion. Okay, next state change. So how big is our sorted array? 27, 42, that's sorted. So that means 19's grabbed, and then these three values will be in different spots. Selection sort, right? So only the smallest value will swap. So 12 and 27. Merge sort, right? Which is first incorrect. So we have 8 values. So the first half will be looked at. So these first 4 values would have been split in half, and then these 2 values would have been split in half, and then we would have these 2 lists to merge together. So 57 and 75 should have merged together, right? So bolded, kind of hard to see in the black background here. Then 1935, right, would be the next sort of list. Then these 4 should merge together. So 19 is correct, 35, 57, 75. So that's good. That's our sort of list. So next up would be this side, which should give us our 14 and 81. And only our 1481 merged together from these 2, but these changed too soon. So line 4 should not have changed yet. That should have been the next state change. All right, 14. Pivot selection. So for pivot selection, we either have the first, the last, or the middle being selected. So our basic selection is we just take the first one and run with it. Our second selection is we just take the middle one and we run with it. And our third selection is we consider all 3 values and we take the median of the 3. So the median of 7, 22, and 28 is 22. Right, if these numbers were in different orders, if this was, let's say this was, 19 over here, right? If it was 7, 19, 22, then 19 would have been selected. So 2 of the algorithms may have selected the first position twice, but as it stands, these 3 specific values could have been selected. Okay. Right there. I need 1 second. I need to go put some drops in my son's ear. Be right back. All right, any questions?
For the bubble sort, why doesn't 27 move if 19 does?
Let's see, the bubble sort. Right, so the bubble sort compares these first two values. 27 is less than 42, so there's no movement here. And then 19 compares with 42, and then there's movement there, and then we keep going to the right, right? We don't backtrack here until the next iteration through the array.
So it only runs one iteration of bubble sort.
Yes, the question is only asking for getting the next value sorted. Because remember, the bubble sort takes the largest value from the unsorted part and then moves it up, right? So in this particular question, the unsorted part is still this part because we have the largest two values over here at this point, right? So basically, we're on the third iteration of this array being sorted with bubble sort.
All right, thank you.
Mhm. All right, see another question. 14, first, middle, last. 14. Those are the three possible indexes that could be selected. First and middle are always going to be an answer for this question, and the third one might be an answer. Because if the third one is not the median of those three values, then it would not be selected. Now, there's no mean. It's a median, right? Mean is adding the three numbers together and then divided by the three. That is not what we're doing here. We're taking the three numbers, ordering them, and then taking the value that is in the center. Right. If the last index is not the median of those three values, then there will only be two answers for this question. Where in this will we find bubble sort? Let's see. Bubble sort. It's going to be sorting bubble sort. 2, 1. Any other questions?
I was also a bit confused on the binary tree lab on what it was asking specifically for the array-based one.
Yeah, so the add is just array sub count equals value, increase the count. So you can basically, the add function is one line. And then the print function is a recursive traversal.
Okay.
Yeah, so no, there's no functional notation on the test. Functional notation was a test one item and then final. When we get to that in 12 weeks, 11 weeks, somewhere thereabouts. Can the array for the tree lab? Yeah, fixed size. That's dynamically sizing arrays is generally something we don't have to worry about. You want to make it a more capable class and be able to size itself, that's perfectly fine. It doesn't change the nature of the structure per se, or the contents of understanding how it works. That's just arrays in general, which is why some people are already trying to use vectors as their backing store for the array when it should actually still be an array, but it's really not that important to the tree itself. So it doesn't matter for the labs.